l'aspettavano così?
Perché credo in quello che dico.
Questo e basta?
Sì.
Don Giussani ha generato un popolo e io faccio parte di questo popolo.
L'avvenimento in cui Dio entra nella nostra esistenza e tutti, colpiti da una curiosità, sospendono per un istante l'ora e guardano dalla parte da cui viene il grido.
Perché l'aspettavano così?
Perché credo in quello che dico.
Questo e basta?
Sì.
Don Giussani ha generato un popolo e io faccio parte di questo popolo.
L'avvenimento in cui Dio entra nella nostra esistenza e tutti, colpiti da una curiosità, sospendono per un istante l'ora e guardano dalla parte da cui viene il grido.
La civiltà dell'amore, fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Buonasera. Good evening. Good evening, ladies and gentlemen, and welcome to this session that will take us much far away. This year's meeting focuses on passion for the person, and this evening we are going to talk about, we're going to see things that are very, very far away from our daily existence, from the dimension that characterizes life in our planet, in our everyday life. And we will explore the depths of the universe. It might seem a little bit unusual having the focus on passion for the person and then looking at far away from the person. But I think that there's something that is really striking and coherent in this kind of choice. Because passion for the person, I believe, brings with it and drags with it passion for the entire reality, for every aspect of reality. Far until the faraway shores and its vastness and its beauty, nothing is a stranger to human nature. Nothing is foreign to human nature. This is a quote that I admire so much by Father Giussani, and it reads, "Human beings are the level of nature in which nature becomes aware of itself." So everything that exists in the universe, somehow we may say that is waiting to be reached by human observation. There's nothing that is foreign potentially to this sight. And certainly for us involved in this profession, we have this desire, this longing for reaching reality, even where it seems to be unreachable and invisible. Up until the last star and the last galaxy of deep universe, as we will see during the course of this session. Well, the meeting of Rimini has always been very interested in science, and this is due to the opening to science and to nature in all its dimensions. And science has its limitations due to the methods that it can use, but it is one of the most fascinating and striking ways to be in a relationship with the world and with reality. So in this session, we will deal with one of, and I wouldn't dare to exaggerate now, one of the greatest scientific endeavors of human history. We're talking about the James Webb Space Telescope. The acronym JWST will be mentioned frequently. So the James Webb Space Telescope was launched last Christmas on the 25th of December last year, and it's the successor of the Hubble Space Telescope that has been offering a great amount of results for 30 years. But now, today, we are at the beginning of a new era, we can say so, of astrophysics and of science, with daring technological innovations and ingenious technological innovations. This tool, as we will see this evening, has already opened a new window on universe. It allows us to see galaxies that are being born, stars and planets that are being born, and we start probing the atmosphere of some of these planets, perhaps finding some traces of life in other parts of the universe. So new questions, new possibilities of knowledge are opening up before us. And most importantly, what matters is that we will get familiar with this new reality guided by the protagonists of this endeavor. Because literally today, we have here with us the people that had to bear the greatest responsibilities in this project. So we want to be guided by them throughout this great scientific projects and the first scientific results, but we also want to hear about their experience and see how this could be possible, how this has happened. So I would like to introduce the guests we have here tonight. The first guest I am going to introduce is connected with us. He's there on the screen. Professor John Mather, Nobel Prize for Physics. John is connected from the United States, but he was here at the meeting in 2009, so he knows the atmosphere of the meeting and he is experiencing it even if from a distance. He is a senior astrophysicist at the NASA's Goddard Space Flight Center. He obtained his PhD at the UC Berkeley in the 70s, and since then he's been studying the cosmic microwave background, the luminous residual of Big Bang, and then continued to study this great, incredible subject, proposing and creating the COBE, the Cosmic Background Explorer satellite, launched in 1989. And this satellite measured with extreme precision the spectrum of radiation and discovered the anisotropies in the cosmic background. These are really one-of-a-kind discoveries that led him to be awarded the Nobel Prize in 2006 for physics. Consider that in 2007, the year after that, John was included by Time magazine in the list of the 100 most influential people in the world, just to give you an idea of whom we are talking about. And in 1995, that is 27 years ago, NASA selected John Mather for the post of Senior Project Scientist of the James Webb Space Telescope. So he's been working for 27 years in this meticulous job of literally thousands of people to create this incredible tool that we have tonight. So we're going to talk about tonight. Thank you, John, for being here with us. And then Elena Sabbi.
Con la fiducia.
Elena is Deputy Head of the Science Mission Office at the Space Telescope Science Institute in Baltimore, where she works as staff scientist since 2013. Her main scientific interests concern the formation and the evolution of stars and clusters of stars. She conducted different research programs with the Hubble Space Telescope, that is the predecessor of the telescope we are going to talk about tonight, in particular on the Tarantula Nebula and in star formation in nearby galaxies. Until now, she has studied these things with the Hubble telescope, and from now on, she will be able to use this new tool. She obtained her degree and PhD in astronomy at the University of Bologna, and I am proud to mention that, as you might have read in the program of the meeting today, 2 out of the 3 guests that we have today are Italian, and they have been educated in Italy, in our universities, and today they control the most important tools that are on board the JWST. Elena, still in Baltimore, also worked for the European Space Agency, in particular supporting the latest repair mission of the astronauts that went to repair the Hubble Space Telescope. She was also responsible for the Wide Field Camera 3, the 3rd generation of this tool, still on board of the Hubble Space Telescope. And over the last 3 years, Elena chaired the NIRSpec team, near-infrared spectrometer that possibly is the most complex tool on board the JWST. Thank you, Elena, for being here with us this evening.
Massimo Roberto.
Massimo Robberto, friend of the meeting, because you've been here so many times, I can't even remember how many. And Robberto works in Baltimore too at the Space Telescope Science Institute, and he's in charge of NIRCam, the tool that produces most of the images that we have seen, and we will see some of them, we will see them this evening on board the JWST. Massimo is also a researcher at the Johns Hopkins University. He's one of the greatest experts in the design, development, and use of infrared astronomic tools. That's the special feature of this new telescope, space telescope. He has been in charge of the infrared channel of the Wide Field Camera 3 of the Hubble Space Telescope. He conceived a possible mission that's called Space Mission that then was included in the Euclid mission of the European Space Agency, and he is principal investigator of the IR Scorpio and Samos tools that are installed on big telescopes in Chile, in the Andes, in high altitude. His main research interest concerns the formation of small mass stars and of planets. He guided several programs on HST, and it is interesting to mention that one of these was concerning the Orion Nebula. That was really interesting, and he analyzed some images that can be seen in the exhibition that we have here at the meeting, and according to the National Geographic, these images are among the most beautiful images ever recorded by the Hubble telescope.
Ha lavorato.
He worked for the European Space Agency for the Hubble program at the Max Planck Institute for Astronomy in Heidelberg, and initially at the Astrophysics Observatory of Turin, the city where Massimo obtained his degree and PhD.
Bene.
Very well. At long last, we can give the floor to our guests, and I would like to ask each of them to introduce, as far as possible in the short time they have at their disposal, to introduce us to this novelty. Why is the JWST a real breakthrough? Why is it a real step forward that is so important? Why is there something unique in this project? So first, I would give the floor to John. Thank you.
Well, my goodness, thank you so much for the lovely introductions of all of us. I am so thrilled to be able to talk with you, and even though I'm not there in person, I do remember very well being there in 2009 and speaking to many thousands of people. So I will show you, I think that you have on the screen my PowerPoint. So what I want to show you is, what is this great project and why are we doing it? So what I hope to be showing you here on the title page is the telescope itself. We see a great golden hexagon. It is 6.5 meters across. It is protected from the heat of the sun, the earth, and the moon by a 5-layer sunshade, an umbrella, as large as a tennis court. This project has been in progress since 1995, as was mentioned, and it is a huge project. It has taken 20,000 people to make this project complete and to set it to set it going in space for another, we hope, 20 years at least of additional observations in space. So I name here some very special people. Our project managers, Bill Oakes and Scott Willoughby, but they would be the first people to tell you that we are not stars, we are team members, and that all of us have done this together because we wanted to. It was our gift to humanity, and also just a good moment to thank the people of our many countries who have supported us through all of the difficult times that we had to solve all of the problems that we had in preparing the observatory and making it work as beautifully as it does in outer space today. So I'll talk about why we are doing that. So as Marco mentioned, we started this Cosmic Background Explorer satellite to observe the early universe. He mentioned that we found the anisotropy, the hot and cold spots in the Big Bang radiation. So this is a map of the sky as it would seem to you if you could see millimeter wavelength radiation, which is actually beyond our capabilities, but we can build electronic devices to measure it. So this is the synthetic map of the sky. It's showing the universe as it was when it was about 400,000 years old. When we made this map, Stephen Hawking said that this was the most important scientific discovery of the century, if not of all time. The importance for science is this tells us why it's possible for us to exist here on our little Earth. This tells us the initial conditions of the expanding universe, and now we would like to know, well, what happened next? How did these hot and cold spots, at a time when there were no stars and were no galaxies, how did they become the modern universe with stars, planets, galaxies, and people? To ask this question and to become aware of this universe that we are in with its magnificent and terrifying beauty. So, of course, now that you've got an observation of the Big Bang itself, what is the next tool that you need? The Hubble Space Telescope was launched a few months after the Cosmic Background Explorer satellite, and we took it into space on the space shuttle. We soon found out that it was not in focus, and we had a terrifying job to do to figure out what was the trouble and how to fix it. And so astronauts have been up to visit it 5 times. First time to repair it, and the other 4 times to upgrade it and make it continue working. It is still working, even though it is 32 years old and still answering questions that we still have. So after we got it working and we studied what we got, we came to the conclusion that even though it was so wonderful and powerful, it could not answer all our questions, and astronomers asked for another telescope, which I will tell you about. So first I'll show you how it went up into space. This is the launch on Christmas Day, December 25 of 2021, from the launch base in French Guiana. And it was a perfect launch. This is a typical launch for the rockets. They go up, in this case, straight to the place where we wanted to go, called the Lagrange point 2, orbiting the sun with the Earth. And of course, this is always a scary moment because even though you have done great work, you do not actually know that you've thought of everything. But it worked beautifully. So here is where we sent the observatory. We sent it to orbit around a place called the Lagrange point 2. It is 1.5 million kilometers farther from the sun than we are, and it follows the Earth as we orbit the sun, so it's always there nearby. It's the same distance away. It's a great place to put a telescope, and in fact, we have several that we have sent there, and we are planning to send several more. So it's a great place to go, and we can talk to the telescope every day. This is the scary movie that we made to tell us what was going to happen after launch. Within a few minutes after the rocket let us go, we unfolded the solar panels so that we could have solar electricity and run the observatory. Soon after that, we turned on the antenna and pointed it back at Earth. Now, it took us actually 2 weeks to do what we're now showing you, unfolding the telescope with its great umbrella, which we call the sunshade, separating the telescope from the warm part of the spacecraft, unrolling the covers to protect the sunshade, And when you look at this picture and you would say, that is an extremely complicated system. And you would say, well, why did you build it like that? And the answer seems to be there is no other way that we know of to get at the scientific questions that we are asking. So naturally, we were all very worried about this because it's so complicated and there are so many ways that something could go wrong. To make sure that it would work, we tested this unfolding many times. And whenever we tested it, we watched it carefully and we found mistakes and we fixed them. We also made sure that there are two ways to accomplish every task, just in case one of them isn't working. So there it is, as it is now unfolded and working in outer space, but of course no human being has ever seen it like this. This is a completely robotic observatory. No human has been close to it, and no human is planning to go there in space. So why is it possible that this telescope is so much more powerful than everything we've ever done before? Well, the first thing is, it is, of course, much larger than the Hubble. The telescope has a diameter of 6.5 meters. The Hubble has a diameter of 2.4 meters. It is also a telescope in outer space. There is no interference from the Earth's atmosphere. And of course, here on Earth, the atmosphere absorbs light from the sky. It prevents us from seeing. It also glows rather brightly at infrared wavelengths. So a telescope in space is required to do the next great step. So even the Hubble Space Telescope cannot see it because it emits infrared light itself. So we cover the wavelength range from 0.6 micrometers to 28 micrometers. Now, 0.6 you could see with your eye, but 28 micrometers you could not. There are three reasons why this is very important to us. Number one, the most distant galaxies that we are interested in to understand the history of our own galaxy appear to us to be red or even infrared, because as the light travels through the expanding universe, the wavelength expands also. So we need an infrared telescope to see the visible and ultraviolet light that were emitted by those first objects. We want to be able to see infrared because it comes from objects that are too cool to emit their own visible light. And it also comes from objects that are hidden by dust clouds. The infrared light can go around dust grains much better than visible wavelength light can do. So we had in mind four great scientific kinds of questions to ask this telescope to address. First, what happened after the Big Bang? What are the first objects that grew? Were the first black holes there in the very beginning? Were they formed soon after the beginning? Were they formed by the galaxies? Did the galaxies form the black holes? So there's something astronomers call the cosmic dark ages. This is the time interval after the expansion began, but before stars and galaxies and other objects could light up and begin to send out their own light. So we don't really know when that happened. It's one of the first and most important questions of the Webb telescope. When were the first stars formed? When were the first galaxies formed? When were the first black holes formed? We think that the Milky Way, our home galaxy, which has got 100 billion stars in it, was actually assembled from thousands of small pieces by the influence of gravity. And we see this in the simulations and the movies that supercomputer people can make for us. But is it true? We have to understand by measuring. The universe is so strange and surprising in so many ways that we just have to look. How are the stars being born today? We know that they happen close by. We know that they happen currently. We know that they happen in that Orion Nebula that was mentioned earlier. And you can see that spot with your very own eyes, or at least with binoculars, because it is an example of such a location is the middle star of the sword of the constellation Orion. Finally, where did the planets come from? And is it possible that any of them could support life? It's too soon to know whether any of them do support life, but we're beginning to develop the techniques and to develop an understanding of where to look. So this little picture in the image shows you a little star orbiting around another star. This is a little planet orbiting another star. And our problem, of course, always is that this splash of glare from the central star is so bright. So we have our methods, which you will hear more about, to measure in different ways besides just looking to see the planet itself. So you'll hear more about those objects from other people. But anyway, I just wanted to show you one of our first and most beautiful pictures. This is the one that was released to the public by President Biden on July the 11th. And you'll hear more about it, but it has stars in it. This big, beautiful thing with the spikes sticking out is actually a nearby star. We have some very, very, very bright and distant galaxies here in the middle of the picture. And we have some strangely shaped objects which seem to be arcs of circles. And these are the result of the gravitational lenses that are in this picture. The gravitational force of this great set of galaxies in the middle is able to bend the light from more distant galaxies and to magnify it for us so that we can get much more information about those most distant things. So now I want to show you also another example, just because it is beautiful. This is a picture of a galaxy as we have never seen it before. The galaxy that we've known before occupies the central section of this picture, and the longer wavelengths information that we get can be processed so you can see the results of new formation of stars. This now looks like a slice through a sponge. And the reason that there are bubbles in the sponge is similar to the reason that we see bubbles in space. There's something with the pressure of a gaseous material which is pushing the material away from the centers of these bubbles and compressing it at the edges. So this is a way that we can learn about the formation of stars on a galactic scale. And I'll show you also a brand new picture. This just came out yesterday. This is a picture of Jupiter as we have never seen it before. Of course, you know that Jupiter was discovered on January 10th of 1610 by Galileo himself. What did I say? This is the satellite Europa, which was discovered by Galileo himself. And what we see now is a number of surprises. Number one, we see that Jupiter has auroras. These orange regions in the picture show that electrons accelerated by the electromagnetic field of Jupiter are crashing into the top of the atmosphere and making it glow. So this is like the aurora borealis that we see here on Earth, but it's very much brighter. It is so bright that we can see it from here. And of course, you see the famous red spot, which is not red in this picture, but we're just gradually beginning to learn what makes it possible for such a thing to continue. There is a satellite of Jupiter called Europa. I'm sorry, I confused myself a moment ago. This is the satellite which was discovered by Galileo. We are very interested in it because it has an ocean covered with ice. And there are places between the cracks in the ice blocks where water comes out. And occasionally we would see that from here using the Hubble telescope. We will be watching to see whether those happen again, and we can see them with the Webb. Eventually, NASA will fly a small probe through those clouds of water to see if they have organic molecules, suggesting that perhaps the ocean on Europa is alive. Just to conclude, there are many ways you can follow the work of the teams. Of course, the typical social media are always alive and alert to tell you what we're doing. And thankfully, the regular press is picking up our pictures every day as well. So I thank you for supporting the project all these years through your agencies and your public interest. And I think we'll go on to our next speakers so you can hear more about what we've actually seen.
Grazie, grazie John.
Thank you, John. I believe that we sort of grasped the scope of what we are talking about. So now let's go ahead with Massimo. Can you tell us a bit more about NIRCam, your tool, your favorite tool, so to say? Right, I'm going to talk about NIRCam. NIR means near infrared camera, and camera for us astronomer is a camera to take picture, and infrared, it means that it works with wavelengths that are close to visible but beyond what our eye can perceive. And NIRCam goes from 0.6 to 5 microns. So it covers an important part, but not all what Webb can do. That gets to 28 microns. The first thing I want to do is to make sure that you can understand why we work in the infrared. And I would like to mention 3 reasons. Number 1 is that interstellar dust that fills the universe, in particular our galaxy, becomes transparent. So we can observe phenomena, stars, galaxies, and universe beyond the screens that we have in front of us. This is a picture with Hubble in the interstellar region in the near infrared. Now I show you a picture in the near infrared. You see that we can enter the cloud and we can discover phenomena and stars that are far away. The field is full of stars. There is a weird object, which is a newly star that is being formed with some objects to which we will go back in a few seconds. Then the second reason is that in infrared, the colder stars become bright. We would become bright ourselves if we had the right tool. Here you see one of the first images took with Webb to the right, and the image of Hubble to the left shows you a bright star. It's almost impossible to see the cold companion that instead the Webb telescope is able to reveal with extreme clarity. So the possibility to study cold objects, cold star opens up, and we can find these at the beginning or at the end of their life. So very short stages, but extremely interesting stages for us. So it's an important tool to understand this star evolution. And then the third reason is that with the infrared, we can see the expanding universe. The light of a close galaxy is received as if it were here in front of us. But as far as this gets far, it has to go through a longer space. And so in order to go upstream, there is this expansion of space and distance getting bigger and bigger. So the wavelength of light increases and shifts to the red. So it means that the image of a nearby galaxy, if it is pushed away from us, it becomes redder and redder as far as light can get to us. I would like to emphasize that the more galaxies are far away, the smaller they get. So we would see something like this, a very feeble and far away object that is totally redshifted. And Elena will say something more about this. So how does Webb work? It's a telescope. It can gather the light streams that get through the universe for billions of years. So they get to the telescope and they are captured into specific points. Every flow gets a particular point, and different stars delivers different flows of light, and all those little specks and dots becomes an image of stars. So once the telescope is ready, the interest lies in analyzing a particular speck, a particular dot, and all the tools are behind the mirror of the telescope. Here you can see the structure that was built with all the tools that have been installed in the Webb. The NIRCam, the near-infrared camera, is the tool in the middle, and if you could look at that in detail, you will see that this is the structure in which it is built. It's like 2 plates of a special material on which these optical tools are mounted to analyze light. Why 2? Because the tool has a double tool. It's not just a camera, it's also a chance to keep together the 18 mirrors that constitute the structure of the telescope to ensure that altogether these mirrors form one surface that is aligned, and to do so we need special optical tools. If NIRCam gets broken, it is hard to keep the telescope together and to use the other tools. So NIRCam is built into two versions. One camera and one is redundant to ensure long life to the telescope. And for us, it provides double the data. So NIRCam structure is double, as I told you. So here is how you can see it now. It is a collection of boxes and cables, and God knows what's in there. To understand how it works, so you see here the pattern of light captured by the telescope entering and propagating through these boxes. From top right part, it is mirrored a couple of times, and then it enters the central part where you can see a red and blue light separating. That's a sort of magic mirror, and it separates the shorter wave radiation, the blue one that is shifted to the right, and the longer one is then delivered to the other part, and so they reach these modulators in a different way. It is a simple tool, this spectrographer, but technically to build it, it's really, really complex for the degree of accuracy that is required working with these wavelengths in space where light gets to us undisturbed, and we do not want to degrade the signal. Everything works at 230 degrees Celsius minus below zero, so there's no way to repair it and to adjust it. So the effort to build these machines have been really immense. It took many, many years. It's marvelous, the technology that is behind this system. What do we get with NIRCam? These are the first images that we obtained, the very first image that would deserve to be observed. And we really liked this picture, even if it is a terrible picture, because here we have the 18 mirrors that are still disaligned. Every mirror works by itself, and we are observing a field that is very rich in stars, the Magellan Nube cloud. So it's a lot of images that do not overlap, and this told us that the tool was working, the light was going through, the revelator were working, and there was just the issue of aligning everything to create the image as we needed. This is what happened during the 6 months after the launch from July until June this year. The 18 mirrors have been captured, so to say. We understood where every mirror was pointing to. The picture to the left recalls the design of the telescope, and they were aligned and readjusted with repeated operations, and it took months, but it was possible to create an ideal image as we expected. That is the one to the right. This is the image in bigger size, and it generated applause and awe in the control room because the image of the star is spectacularly on focus and clear, but we can see that there is also the background universe that is full of galaxies. So the sensitivity of this tool is so high that we can see deep universe anywhere we point it to. The same object observed with the best infrared tool built before Webb is this. So with a bit of imagination, you can find a couple of galaxies to the left and below. Of course, you see the difference, and this opens up new extraordinary horizons of knowledge. This is the first field picture with the telescope working properly, and we can have full evidence that the telescope was working well. Once the telescope was set up correctly, we wondered where to point it and to get some interesting target so that we could demonstrate to us, to the public, and to the colleagues that everything was working well. We took some sources, and I'm going to show one of the most spectacular, a region of stellar formation. It's not far from us, about 7,500 year-lights, near the Carina Nebula. This is where it is in the galaxy. We are outside the center, and we are looking around, basically. This is a picture of the region. It's a big region of stellar formation. We took a peripheral edge, this small bubble, to the right bottom hand corner. We observed that with the telescope, even if the field of our camera is quite big, we can see only a small section, which is the one in this red square. So Webb was pointed there for some hours observing that part of the sky. That's the image that we could build out of this region. We have this spectacular edge of the gas nebula. The top part, there is emptiness, and the cavity that was made by the light of the bright stars, and then the surface that was worked below. I show you in black and white because that's how we work. We don't have pictures in color. We normally work in black and white, and then we apply filters. Here you see 3.35 micron. It's a filter, relatively blue filter. So if we paint it in blue, that's what we obtain. That's the same picture colored with a computer. And if we change filter and we paint it in gray with the 4.44 micron, we obtain another one. If we change filter at 4.70 micron, we obtain a different image. All these pictures in black and white are colored. They are combined artificially by us to obtain a color picture such as this.
Shade.
Of course, there is a trick, because this trick is not just a result of 3 pictures, but 6 pictures. Why? Because of the mirror I mentioned before. Half of the picture goes to one channel and the other half to the other. So when there is one half from the blue channel and one from the red channel, it's 2 for the price of 1. So why not using it? So when we combine 6 pictures, our artists can build pictures like this. So 1 minute to show you what's in there. We could talk about this for hours. This is the region where in the cloud where stars are formed is being eroded by the ultraviolet light of very bright stars that are outside the field. You can see some part of the sky that is not totally clear. This is the wind that erodes matter. This is an ephemeral phenomenon. At the end, this cloud will disappear, and only the stars that could form there will remain. We are seeing the phenomenon of destruction and formation of molecular clouds. Of course, erosion is easier where material is softer, matter is softer, but there are some parts where density is working, and it's having more resistance, performing more resistance, and there's more things to erode and to dig away. So you see these spikes that are really spectacular, and easily we will find inside these forms some small stars that are being formed, because that's where gravity tends to condense more. So we see directly, we see the points of the region where stars are being formed. And there is great variety here. We had 2 more cases that are weaker, not so evident, but equally spectacular. For us, it is a kind of zoo where we look for stars one by one to carry out further studies. The interesting thing is that when some stars are formed in these cavities, it is a sort of race against time, because we have to find them before everything gets destroyed, because a star can make it and gets formed, but in a perversive way, the star starts self-destroying, because star starts throwing material out, and these jets of material from stars being formed are still mysterious phenomenon of star formation. The gravity forms the star starts expelling parts of its material that should get inside, but instead is thrown out. This is what is seen with a lot of details, and it's interesting to understand the time schedule. This is another image to show that the sky in the background gets filled again with galaxies. So we break through the limits and we keep seeing galaxies in deep universe. The last point. The color pictures are beautiful and they entertain the eye. They let us understand many things, but how do we watch these images? The last point to introduce Elena's work. We watch this, we look at these images in black and white, and we consider them as three-dimensional. We imagine light as a sign, and it is a sign that creates pyramids of lights such as towers or bells. The signal is three-dimensional. I try to represent the data as they arrive here. Every point of the sky can give us some density, some numbers, and our art is to try and measure what happens inside these pyramids or these light pikes. It's like the fingerprint of a telescope. Sometimes they appear, other times they don't, and they change depending on wavelength. So the art is to do all these measurements, put them together, and connecting all the dots, finding the physics, the spectrum, and the signal that can explain them. 3, 4, 5, 6 dots, each per wavelength. This is the art of analyzing astrophysical images. Of course, we have to analyze the spectra, and the ideal would be to have all the information, not just 4, 5, 6 dots. We have dots for thousands of objects, but for some objects, we would like to have all. That's what a spectrographer does, and that's the tool that Webb has implemented. It's our brother, so to say, to study in detail the most interesting sources. That is the tool that Elena will present now.
Bene, io ho un compito un po' più.
Well, my task is more difficult because I need to attract and captivate your attention, not with images, but with spectrums. And sometimes people say that an image is worth 1,000 words, and we have seen that this is true. But before going on, I would like to remind you of the fact that with our naked eye, we can see just a little part of the light and the colors emitted by the sun and all the other stars and galaxies. So they go from radio waves to gamma ray and X-ray. We know these names, but they altogether belong to the electromagnetic spectrum, but with our naked eye, we can perceive just a little part. Webb opens up a new horizon because you see the medium and near infrared, so from 0.6 to 26 micron. Astronomers do not look at the whole light coming from an astronomical object because that would be too confusing. Here you see a planetary nebula from Hubble, and we see false colors. It's not the whole visible light that are represented with the rainbow below, but it's the composition of three images. One is sensitive to helium with a very short interval, so a little strip of colors. And what we see here is just a set of little dots. These are stars, and a slight nebula at the center. If we have a look at the same region with the oxygen wavelengths, we see that the central part of the nebula lights up. And if we look at hydrogen, we see that mostly it is distributed in the periphery. So if we look at the same object with different filters, you can understand how the elements are distributed in outer space, and we can understand how it expands. And so we have the explosion and then its evolution. If we combine images, we get the final beautiful results. So we see different contributions overlapping. And as Massimo said, With this trick, we lose a lot of information. We don't know what there is between the red and the green and the red and the blue. But instead, if we take light on a certain interval coming from a source, and we classify that according to the level of energy. So with the shortest wavelengths and the highest level of energy down to the lowest energy areas. If we look at an object with the different wavelengths, let us understand immediately the most energy-filled parts and see how energy varies in the different elements. Secondly, when we look at the spectrum, we see often dark lines. Dark lines are the hydrogen, carbon, oxygen elements that are present in the gas of a galaxy, in a star, and that stole a little bit of the energy that we are studying. These elements have a specific position. Every time we see a hydrogen line, it's always in the same place. The same applies to helium, iron, oxygen. Every time we see a line, we know who is responsible for emitting that signal. If we look at the lines, they have different depths and widths. So if we compare different stars, we can see the abundance of oxygen, of carbon with respect to iron, for instance, or we can understand, the level of gravity in the atmosphere of a planet, and we can understand the temperature. So a spectrum is certainly worth more than 1,000 images.
Perché dovete sapere
You have to know that Elena and Massimo makes jokes about the importance of their respective tools. Which is the most important, the spectrum or the images? Usually, we look at the source with a little slot, through a little slot, in order to see a spectrum at a time. Or we can do something else. We can take an image, like the one John showed us at the beginning, of this deep field, and instead of watching it through a filter, we can disperse the light with the prism. Instead of having aligned sources, well-defined and neat, the whole light is dispersed in spectra that end up overlapping. In order to avoid confusion, we tend to use low-resolution spectra that are quite compact, and this allows us to see that in these very, very far-away galaxies, whose brightness has been increased by the gravitational lens. So we see that there is hydrogen and oxygen. The two arcs that are pretty clear and have the same distance and same chemical composition. It's the same image of the same galaxy produced twice by the gravitational lens. And we can prove this quite clearly by looking at the spectrum. This is a low resolution spectrum. So again, we lose out information. So what we want to do is to have a closer look and see more details. So we can do that with high resolution spectrum and by using a trick. So we put a sort of mesh with 250 little doors that we can open. This is mesh work, and you see a part of these little doors, these little slots. So you have a bar saying 300 micrometers, and we see the size of these little slots. A hair has a diameter of 70 micrometers, so we can put just a couple of hair in each one of these slots, and we can open them individually. NIRSpec was built by ESA, NASA, Airbus. This is not a low-resolution image of all the agencies and entities that work together at this project. This is a lab test, and we individually opened the little slots to recreate the logos of different partners. We can do the same thing by looking at some of the most interesting galaxies in the deep field. We selected 40 galaxies varying for distance and shapes. Some are spiral shapes, the others have the shape of an arc, others are elliptic. Here you see 4 of the furthest galaxies that we have identified. They range from 6 to 8. Red shield 6-8. So light took from 11 to 13 billions of years to come to us. The farthest galaxy appeared like this already 700 million years after the Big Bang. So we can understand how distant these galaxies are simply by looking at the 2 lines move according to the wavelength, according to the range explained by Massimo. So why do we have a better resolution? Well, then oxygen is the blue line, actually is double. So we can see more details. And most of all, if we look at one spectrum, the one of the farthest galaxy, we have more elements. We have neon, hydrogen, oxygen, and we were really moved the first time we saw this spectrum because there is this little oxygen line. This is the aurora oxygen. So this is a line that we tend to use to study the chemical composition of a galaxy, to understand how many elements, how many stars were formed during its whole life cycle. And we were expecting that at redshift 3, we can see it at redshift 8. That means that we can compare the composition of galaxies in chemical terms all through the galaxy formation, and we can see how galaxy evolved and grew during its expansion. So this is the proof that Webb will let us understand how the universe evolved. So far, I've showed you how to use NIRSpec for galaxies, but now I will go on. Another thing that we can do is put spectra in an integral field unit, IFU order. We have now 100 spectra, put one after the other, to study the distribution of chemical elements in the heart of that galaxy, where there is a huge black hole that is eating, swallowing a large quantity of matter, so it becomes so bright. So radiation emitted by the black hole was subtracted to show you to what extent, even if black holes have huge masses, you can still see objects and matter that is expelled. We have 2 jets, one pointing upwards, the other downwards, and you see the brightest points where the jet clashes with the material surrounding the black hole, and because of the shock, it becomes bright. This is the image without the central GN. So just to show you how spectra are different, we have a viscous disk in the central part. Matter is falling on the black hole, and we see a wide silicate strip. It's the green line. On top, we saw the spectrum of the object being launched in outer space. There are some thin lines, all emitted thin lines. This is a frequently asked gas, like neon gas, that is still present in some specific older facilities. We can also have a look at the different elements and map them, and we can see how these lines move either in the red or in the blue, to understand how gas moves around in space. A line towards red wavelengths means that the object is moving from us. If they are in blue, the object is moving towards us. These are maps of argon, neon, and molecular hydrogen being colored according to their motion in space. Blue gets closer, red gets farther. We have a different speed of 400 kilometers per second, not per hour, per second. And then, as I said before, we want to use NIRS because we want to study how stars form, where the building blocks needed to create life are, to transport molecules like hydrocarbons and water on planets like Earth. And on top of that, and in my opinion, this is the most spectacular thing that Webb can do, we can study the atmosphere of the planet. And Massimo told you that we launch satellites there because we want to avoid the atmosphere of Earth. So the satellite can reduce the light of stars, but generally it can mitigate or steal some colors from the star's light because there are chemical elements in the planet atmosphere. If we subtract the star spectrum from the planet spectrum, we can see the spectrum of a planet's atmosphere. We tried to do this with Webb, and we looked at a planet on which, thanks to Hubble, we thought there may be some water. And in a very short time, just a couple of hours of observation, Webb showed for real, as a final version, that there is water in the atmosphere of these planets. So we will see planets similar to Earth, to Jupiter, and to Neptune. So these are not the Webb spectra, these are just simulations, but this is to show you to what extent temperature differences and the gravitational differences can vary the shape of a spectrum, and right after we can interpret what we are watching. So once again, a spectrum is worth more than 1,000 images, and NIRSpec can somehow produce 250,000 spectra. I do apologize. You need an image in order to understand where to take the spectrum from. Okay, I think that we had an even better understanding of the news that are upcoming. Now, I would like to ask you a quick question of a more general, or a more personal nature. Okay, we all realize that to get to these first results, to first of all get to launch the tool and calibrate it and make it functioning and gather this first data, it took so much time, decades, and it was a risky journey. There was such a high level of complexity when John showed the deployment with those screens, those panels just unfolding. Wow, it's incredible because so many things can go wrong. And so how much rigor, how much patience, how much trepidation. So my question now for all of you is, could you please tell us what sustained you all through these years of work, of difficulties, of tension? Let us know maybe about a very difficult moment you have overcome, maybe a very difficult moment or an extremely passionate moment. Massimo, you can start.
Well, critical moments there were indeed. There were critical moments linked to technical hitches. Sometimes there were things that were not working, sometimes in my tool or in other tools or in the telescope itself. But as you were saying, perhaps the most challenging part was the time passing by. And John can confirm this with precision. Every 2 or 3 years, we were just postponing over and over again. We're not launching in 2007. We're launching maybe in 2003. I don't know. Maybe the first launch had been planned in the early 2000s, but every 2 or 3 years, we were postponing this moment again and again and again. So this required a lot of patience, a lot of obedience, and maybe even a little bit of irony among us, and trying to understand that great things require time, require patience, require trust, and also require excellence. And excellence has a price. Excellence requires all of this. This perhaps has been the biggest challenge. I've spent most of my career on this. If it had been launched 15 years ago, maybe I would have done something else too. But you stick to the project there, you keep going and follow the journey where you started to do something great. That's what I think I want to say.
Elena.
Elena, over to you. Well, I joined the project quite late, just 3 years before the launch. I didn't suffer as much as you did. But I joined the project and I was so excited. When I was a student, I was imagining what an astronomer does, and I was saying, well, perhaps they launch a space telescope, and I found myself being part of a team that was going to launch a space telescope. I was in those meetings where John was talking, and I had goosebumps because I was in the same room with him. And then the pandemic arrived, and this for me was devastating. Working with crazy time schedules and encouraging my team of marvelous people that had to help their children to study from home, and at the same time they had to give a presentation before the director to show the work progress, and they had their children jumping over them and pulling their hair and playing jokes. So my task to motivate continuously my team was really, really hard. It was really hard for me. But then the first time we saw the first star on focus in a place where we thought it was empty of galaxies. It was so marvelous, but every 5 pixels there was a surprise for the eyes. What the Americans say, an eye candy. It was 3 hours where nobody could keep working because we were just looking and looking around and around. It was really, really worth it, and now it's just the time to play with that and discover the universe. John, over to you.
What do you think?
Yes. I have this interesting perspective of having worked on this project for all 27 years. And to tell the truth, I was never suffering. It was always a work of joy and happiness to work with this team. So no matter what happened, I thought this is a project which is unique in history. There is no other way we can ever accomplish this scientific set of discoveries that we're hoping to make. There is a little book called HST and Beyond. It's a committee report from 1996 that tells us why we should build this observatory. And it is so thrilling to read that little book. It is wonderful. It says we are doing something that is absolutely worth all this effort, no matter how hard it is. So that was my understanding, and I thought, well, I'm just going to work on this project for however long it takes until we succeed. So we have been blessed by the support of our public all these years, despite all of the delays. So I always look at that, and I think what a wonderfully creative team that we've had to be able to make that possible. So I have this tremendous feeling of appreciation and affection for the people that I work with.
Grazie. Un'ultima.
A last round, just to finish our conversation. So we're going through difficult times at international level, and we have had several occasions, even during these meetings edition, to think over some difficult situations and the reasons that we still have to hope for the better. So, considering these times we are living in, what do you think about your work specifically? And such a scientific endeavor like the JWST could give a good contribution to humanity? What's your take on this? Elena, you can start. Well, we already said it, I think, but Webb is the result of an amazing partnership between Europe, the US, and Canada. Dozens of countries joined the project, hundreds of industries, and 20,000 people who made this possible, thanks to their devotion in 27 years of work. So undoubtedly, this requires a huge level of cooperation among people in order to create these terrific scientific objects. So several countries need to join forces, but also Webb images show us that we're just a grain of dust. I mean, we're teeny-weeny. We are living on a grain of sand, so we need to take better care of it, maybe. That would be the case. Massimo. Well, I don't want to repeat what Elena said, and she was so right in everything she said. Personally, thinking and looking back and thinking about what we're going through, I realize that I somehow got used to, being surrounded by excellence. I'm so lucky because thanks to this project and to this work, I'm just familiar with the top experts and top professionals. So when I read the newspapers, I don't know, I ask myself, what if we all could live and work at such a high level? I don't know. I think it's important to show how beautiful, how exciting it is to work at such a high level. There are so many great things we could achieve if each one does its job properly, because I'm so used to excellence. Why don't we all work like that? Elena and me, we all breathe this wonderful smell, and it's so exciting. We could do crazy things and get great achievements. So that's what I'd like to communicate. If we join forces, wow, we can do a hell of a work and achieve incredible things. But we need passion, excellence, and enthusiasm, and the passion for doing things right. So listen to knowledgeable people, do the right things, read and get informed, study, and being liable for what you do, for what you say. It's about a whole way of thinking and of doing, implying rigor, honesty, and the beauty of well-done things. I think that's the secret of the success of the Webb project. John, you have the last word.
Yes, I have often thought of President Kennedy, who said when we were going to go to the moon, he said, we are going to do this incredibly difficult thing, not because it is easy, but because it is hard. And in doing that, we will learn how to do other hard things. So we have done that. We have established the possibility of human beings taking on incredibly difficult challenges and succeeding. So I see the bad news that we see in the news quite often, and I say, and we have done incredible things, and we can do more incredible things. There are so many things that we face as problems and challenges which are based on scientific and technical things that we can address. Climate change is in our power to control and manage. There are scientific discoveries to make, engineering developments to make. We can manage these things, but it does require cooperation of many nations together, and it is possible because it is worthwhile. So I am anticipating that the love of people for one another and for protecting our small, tiny planet will actually win the day, and we can do the things we need to do to take care of it. That's what I hope and feel.
Thank you. A big thank you to our reputable guests for their words, for their scientific testimony, and also for their personal testimony, because they shared a page of history, a very special point in time. We saw really images that are a breakthrough, and maybe if you did not somehow perceive all the technical details, I think that what you could perceive clearly is the enthusiasm of these people who work so hard. And we are seeing things that have not been seen before, never ever. So this is special. And we can see something that has never been seen before, and we see that this tool is working. So again, there is so much wait for what is coming next, because they used to talk for many years about the future, what would, be next. And this is what makes research alive. This makes every human experience somehow worth living, the certainty that the future will unveil itself, because the tool is there. And so this first result is just the beginning. It's just a sort of flavor of something, and also trying to unveil something that apparently seemed to be so far away from us, almost, foreign to us. Actually, it's about opening up a new window on the universe. But to open that window, you need first and foremost to open up your eyes. You also need to open your eyes and not just a window. You need to be ready to see what is new. This applies to astrophysics, to JWST, but I think that this is the most positive and constructive attitude in any, situation of life, opening up the eyes and being ready to what reality will present you with. Thank you. Thank you very much again.
Grazie John. Ciao.
Thank you, John. Bye.
La civiltà dell'amore, fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Perché l'aspettavano così?
Perché credo in quello che dico.
Questo e basta?
Sì.
Don Giussani ha generato un popolo e io faccio parte di questo popolo.
L'avvenimento in cui Dio entra nella nostra esistenza e tutti, colpiti da una curiosità, sospendono per un istante l'ora e guardano dalla parte da cui viene il grido.
Perché l'aspettavano così?
Perché credo in quello che dico.
Questo e basta?
Sì.
Don Giussani ha generato un popolo e io faccio parte di questo popolo.
L'avvenimento in cui Dio entra nella nostra esistenza e tutti, colpiti da una curiosità, sospendono per un istante l'ora e guardano dalla parte da cui viene il grido.